We covered rational numbers in the previous chapter, and in most daily the problems, the rational number is enough to handle that. But in some cases, we need some new numbers. So rational number is not enough to cover that. So most traditional way of finding the needs of these new numbers is done by Taurian. So these people actually find out some very strange numbers, and because they believe that the rational number is enough for handling anything, so actually they try to hide their findings. It's very strange, nowadays point of view, but it's kind of almost a religious group. Okay, so they just cut down something is against their beliefs, but it turns out that they found out it's very famous. Like whenever they have sphere, and doesn't matter what the length are, but like let's say it's 1, then any objects in the world can be done denoted by some number, right? So especially like a number of the length of line segment, yeah, it should be denoted by a certain number, right? So they try to find the length of this one, and you know the Pythagorean theorem. So it's a right triangle. So in that point of view, they should get some number, but it turns out that there is no way they can write down the number. So that was the kind of first instance that the human had before. And another thing in modern world is like if we have any sequence of rational numbers, okay? So like it can, the usual style is just fraction terms, right? P over Q, but that can be pulled out for decimals, right? So how about 0.9 and 0.99 and 0.999? So if we keep doing this way, where does it go? What is the limit of this sequence? It goes to 1. It's so clear. So it should work like this. Problem is, if we choose, let's start with 3 and 3.1, 3.14, 3.141, and keep doing it. Yes, so we know where it goes, right? So it's going to be, the limit of this sequence should be pi, which we know right now, but all these numbers are rationals, right? They belong to that set. But at the end, the number it's approaching doesn't belong to that rational number set. So if we just assuming rational numbers are the only numbers in this world, in this universe, there are some objects which doesn't belong to that world. That's very strange. So we know it exists, then we should include that one in our universe, right? But so far what we have is just only that much, right? So there are some missing pieces. And that's what we are interested about, irrational numbers. And rational numbers, irrational numbers all together becomes the real numbers. So let's just show why that number denote this length of this hypotenuse is not rational numbers. Okay, so to do that, we need some prerequisite in number theory. So you're going to cover this one in number theory, but let me just cover a little bit of it to taste it. Okay. First of all, we already have this one. For any integer is even, then there must an integer exist and satisfying that given number can be written by 2 times of that integer k. Okay. So let's just prove for any n, if n square is even, then n itself must be even, and if n is even, then n square must be also even. It's if and only if statement. So let's prove both directions, right? First, Before doing it, we have to have this one. Let n is an integer. Positive, negative, doesn't matter. And first statement is, for that one, we have to say, let n squared be even. And what is the meaning of that n squared is even? And there is an integer, so let me say k, such that the given number can be written by 2 times that one. I just follow this definition for that. So that's the kind of consequences of that given hypothesis, right? Then we need to prove n is even, so which means n equals to k or something like that, right? But direct proof is a little bit difficult, so let's take the negation of the conclusion and try to show some contradiction. Okay? So let's say n is not even, which means n is odd. That means there is some integer satisfying that n equals to m plus 1. Then let's make it square. And 2m plus 1 squared is 2m squared plus 2 times 2m times 1 plus 1 squared. That's 4m squared plus 4m plus 1. If we factor out 2 from the first two terms, we have 2m plus 2m plus 1. Now, we said m is an integer, then m squared is also integer, 2 times the number should be integer, 2m is also integer, the addition of this number is integer. So altogether this is just one integer. Then the way of given is 2 times integer plus 1, which means what? N squared is also odd, right? So what we just show is, in the beginning, we wanted to prove P implies Q. Right? This direct proof is a little bit difficult, so we just take negation of it, so not Q, and we just show not P, because given condition is n squared is even, but we just show n squared is not even. So this statement is contrapositive of given statement. And in logic, both of them has same truth value. So if one of them is true, the other one should be true. One of them is false, the other one is also false, like that. So from this proof, we just show this, right? Which means what? Its contrapositive is also true. Okay? So therefore, if n squared is even, then n is even. How about the other direction? This is much easier. Let's say n is even. Then now we can use this one, the definition. There is an integer such that the given number is 2 times k. Hence, if we make it square, we need to have that, which is 4k squared, which is 2 times 2k squared, and that is also an integer, right? So 2 times an integer, which means n squared is even. Okay? So the other direction is also true. Okay? So that's the end of proof. So remember, n is even, n squared is even, definitely, but n squared is even means n should be also even. And using that fact to prove this next statement, Okay, let's prove square root of 2 is irrational. So what is the meaning of square root of 2? You have to understand the meaning of it. In traditional natural numbers, we use those symbols, right? 1, 2, 3, 4. We are so getting used to use these symbols, so we don't feel any kind of uncomfortableness or anything like that when you use this one. But if someone uses 1, 2, 3, 4, I think these symbols are much more reasonable than those, right? This is really showing how many objects I have, right? 1, 2, 3, like that. Right? Even for operations like a plus, I just put those objects all together. I counted and 7, right? So how do you know why this 3 plus 4 equals 7? We know, right? But this symbol doesn't give me any information about it, right? So these symbols are better, right? But we just get used to use this method, then there must be a reason why people use those type of symbols, right? It's just for assigning symbol, not the mathematical behind story whatsoever. So this is not really true, but people believe this is how they invent those type of symbols, right? So in the Egyptian era, people use the most math is about geometry. So when they need to assign certain symbol for number 1, number 2, number 3, they thought about some geometric shapes of it, right? So technically between just you and me, let me say this is number 1, number 2, number 3, number 4, right? Then no problem, right? To communicate with that. So I can show you, I can ask what is that, right? And you can answer like that, right? So that's the symbol for 7 for us. It's almost impossible to redraw again. So simpler is better. So they need some symbols to denote that each number. And it should be geometric shape. Okay, then what is the kind of important ones in geometric shape? They thought the number of angles on it. So like this, that, this one, that. So as you can see here, 1 angle, 2 angles, 3 angles, 4 angles, 5 angles, 1, 2, 3, 4, 5, 6 angles, and they were in trouble for 7, and one clever guy tried to do this way, right? So 1, 2, 3, 4, 5, 6, 7, and 8. It's like this: 1, 2, 3, 4, 5, 6, 7, 8. And for 9, it's like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. And how about 0? Ooh, looks like no angle, looks reasonable, but remember, in Egypt, 0 is not positional number system. That 0 is developed later, much later. Okay, so, but most likely like this, right? So what I want to say here is, what is log 2, 3? Why we use this type of kind of complicated notations? But if you look at that one as the meaning of that number, then this is really reasonable assignment, right, to the symbol. So treat this one as a symbol. Okay? Don't think more. Do not think the method or calculation, right? That's next step, right? Just imagine why people use this notation, and for one number. Okay? So look at here, one number. It's number 1, number 2, right? Okay, then what is this number? Just think that way. Right? Then this number has certain rules. So let's say temporarily, let me assign heart as the symbol of that number. Okay? They are exactly same meanings only. Then what this number do is, if we put that number as the power of 2, the base, then the result must be 3. You follow me? This is the meaning of this logarithmic notation. In many cases, we are wondering about that exponential value to satisfy this. Of course, like if we have something equals 8, then it's easy to get, right? That power should be 3. But in most cases, we don't have that much nice result like integer value. Rather, this result is irrational values, right? Then do we need to assign all different symbols for each different cases? How do you remember this whole thing? No way, right? So there must be some kind of some procedures, right? And it just should work for no matter what cases is, right? I'm sorry, there was some office. So okay, where we are. Okay, let's say so. Like whenever we have such cases, right? 2 to the something becomes 7. Okay, what is the good notation for that, right? Good symbol for that. So don't ask me why, but people saying, okay, let's just use this notation. Okay, log, and this one, so that exponential part should be has this type of symbol. That symbol tell us what we are talking about, right? Not just arbitrarily some useless and some no meaning sign, right? This is really stupid, right? So in this symbol, people saying, okay, whatever that number is, that number makes 2 to the of that number equals 7. So which means if we use 2 as the base of that number, we are going to get 7 as the result. You follow me? Okay, so this is a nice way to defining. Now, what is the meaning of square root of 2? We are so getting used to see it that way, so no one asks that one. But if someone asks you that question, what is square root of 2? Don't say, oh, it's 1.14. You cannot say it because it's infinitesimal. So you cannot say the exact number, okay, by just saying 1.1, 1.414 like that, right? Rather, you have to say the meaning of square root of 2 is some number, right? One number. And that number, if you make it square of it, the result is 2. Can you see how people made that symbol for that number? So then it's easy to explain what is square root of 3. Oh, if we make it square of it, we are going to get 3. So that symbol, that sign, tell us what is going to be the answer or the result of certain operation, right? So it's a square root means what? If we make it square, then whatever we have, we will get that one. Okay? So how do you get this square root of 2? Yeah, from that hypotenuse of this right triangle or something like that. And remember, this is just only a symbol, only a sign to denote that number, whatever it is. So nobody knows whether that is a rational number or something else. Okay? So we start from that position. Okay? We don't know whether it's rational or irrational. But eventually it turns out that is irrational and we have to prove it, right? So when you start it, we just assume, oh, maybe it's a rational number, right? Who knows? Okay? Then, according to our definitions, any rational number can be written by that order pairs 1, but we have a nice representation of it, which is P over Q. Okay? Of course, Q cannot be 0. Okay? So, in this case, let's assign, because we are assuming that square root of 2 is a rational number, so let's say A over B. Then hidden condition is B cannot be 0 by the definition of rational number. Another thing is there are many different ways of representing that number, right? For each single rational number, there are many same related numbers are there. Actually, order pairs are there. So, like if A over B is that answer, then 2A over 2B is also that answer. 7A over 7B is also same, right? So there are many different cases. So all we want here is that's the reduced form. the lowest terms, right? So which means this A, B's are relatively prime, which means there is no more common factor between A and B. Like a 2/3, yeah, that's nice lowest terms, but not 14 over 21, right? Eventually they are same rational number, right? But if we have A equals that, B equals that, then try to cancel out until we got relative prime cases. So that's the big condition for this proof. Okay? Remember that? So if we have that much, then let's make square on both sides. Now once again, what is the meaning of it? What is the meaning of that number? If we make it square, we are going to get that inside number as the result. So if you make it square, left hand side becomes 2 and right hand side is a over b squared. Now you can follow that multiplication formula in the previous chapter for the product of two rational numbers, but in this case you can just use our own method, right? So it's going to be like that, which means 2b squared equals a squared, right? Now then what this one means, a squared is 2 times some integer, right? So it's like a 2 times k. Then by the definition of the even numbers, we have the a squared is even, right? And by the previous theorem, if a squared is even, then a must be even. And by the definition of even, there must be an integer k such that this a can be written by 2 times k. Then let's substitute this result to this equation again. Then 2b squared equals 2k squared, right? Then it's 2b squared equals 4k squared. Both sides is multiple of 2, so divide both sides by 2. Then it's going to be b squared equals 2k squared. And at this time, b squared is 2 times some integer, right? So that means b squared is also even. And by the previous theorem, b should be even. Then what we have right now is a, b's are both evens, so a can be written by 2k, and now b is even, so it can be written by 2m, right? Then when you write down a over b for square root of 2, it can be written by 2k over 2m, which means between a and b, there is still common factor 2, right? So we can cancel out these two, remaining k over m, which means k over m is more kind of simpler forms of a over b. Or you can say a over b is not relative prime because 2 is a common factor between these two. So that's against to this factor when you had, right? So it's a contradiction. So why do we have such contradiction? All the arguments are true, right? We only just accept all the true statement and some theorem we already proved before, right? So the only missing piece is we just simply assuming square root of 2 is rational because we didn't know whether it's rational or irrational, right? So we just assuming that, and turns out, ooh, something is wrong, right? Which means what? This is not true. So negation must be true, and that's the kind of the result, like a square root of 2 must be irrational, okay? So that's the entire proof, and this proof can be applied to any other numbers like square root of 3, square root of 5, why these numbers are irrational. Very similar method, okay? Only difference is something rather than the multiple of like a, not even, but multiple of 3, multiple of 5, or those stuffs, right? But it's the same thing, so you're going to need that one for the homework later. So in this case, so far, we just to check whether the square root of 2 is rational or irrational. We just to prove it mathematically, but we haven't covered what that number is actually, right? How does it look like? Okay? So in here, let's just try to find out what this number is, right? And of course, once again, we cannot get that result, right, as a decimal notation, and there is no nice fraction form to denote, right? So how about approximation, the algebraic approach, right? So someone did it already for that. So he gave this nice recursive definition of some sequences, and let's take the limits of these sequences, right? So if you want to say, oh yeah, how about the sequences 1 and 1.4 and 1.414, right? Then it goes to, yes, we can claim that is the limit of that is square root 2. But in this case, we already knew what the decimal notation for square root of 2, right? And we don't know what the exact decimal notation of square root 2 yet, right? It's only up to maybe 1 millionth position or something like that, right? After the decimal, but not the entire decimal notation. We don't know, right? So it looks like we don't know what this number is, right? As a value, right? We know approximately it's around that, okay? Between 1 and 2, and okay. So let's just try to get that number, right? Okay, how close? Okay, that number should be at certain value between 1 and 2. First, x of n is defined by like that. From the x sequence, one previous ones, right? Predecessor, and y sub n minus 1. Among the y sequence, one predecessor one, right? And yn is double of predecessor of xn and adding the one previous y value, okay, in that sequence. And take the quotient between these two, yn over xn. Then it turns out that the limits of this sequence is square root of 2. Okay? If you let n goes to infinity, then this quotient value is approaching to square root of 2, closer. Okay? And this method, the good thing about this method is actually doesn't matter what number we assign for first two numbers, for x1 and y1. Okay? It's always approaching to there. That's the amazing part. So we can just check first a few terms of this and find out, yeah, it looks like it's closing to the square root of 2. But another good thing about this method is instead of 2, if you use something else, some other integer, then actually the limits of the sequence is approaching to square root of that number, okay? Whatever you assign for that, replacing number 2. So actually this method is really quite good for checking all the square root of some integer value, right? Okay, for the calculation, it requires kind of a lot of calculations, so let me just use Excel file. So look at here, we start from just 1 and 1, and we already mentioned like doesn't matter what number we start with, right? But in this case, just let's use 1 and 1, and we have a formula for that. Okay? For xn, we just adding the previous two xn and yn, right? So this is sum of the previous two values like that. But for yn, we have to multiply 2 for this one, this xn, and adding yn, right? So 2 times this one, right? And plus this one, okay? So we just apply that rule. Then when n equals 2, we have that. Then the ratio between yn over xn, in this case, is 1, clear. and 3 over 2, which is 1.5. So if you keep doing it, next one, adding this, 2 and 3 is 5, and 2 times 2 is 4, plus 3 is 7. And the ratio between these two, 7 over 5, is 1.4. So if you just keep doing it, going further, and if you're doing further, you see that these numbers looks like this, and almost at the end it looks like we got the same number. Be careful, we are using technology which has some kind of limits. So in this case, up to this much is just that Excel could handle right now. Okay? 10 decimal position, right? So if you have better software, then it gives you kind of more accurate results. But as you can see here, this sequence kind of looks like approaching to that 1.41421 like that, right? So that's that number for square root of 2. So you see the video right now, so I think it's easy to fill out those numbers, right? So please just write down up to number 8. Do not calculate by yourself. It's just a simple calculation, but if you're using your calculator, I think it's good. So give me the last result, right? Fine. Okay. Now the next case is, okay, we found some algebraic approach to see what is the number for square root of 2, right? But how about geometric approach? Like, okay, we already have the hypotenuse of that right triangle is square root of 2, right? So we can construct that kind of line segment. But how about square root of 3 and square root of 5, 7? How do you do that? So this is one way we can sketch. So this is kind of typical way to do it. Like from that right triangle with the same length for 2 legs, let's say that is 1. Then the hypotenuse is square root of 2, right? So that itself is a nice construction, but on the real line, where that value is, right? Then you just use the compass, okay, centered at the origin, and sketch it, that intersection between that circle and the x-axis. That's the where you assign the square root of 2 on the points on this real line. And how about square root of 3? Using the Pythagorean theorem again, this length is square root of 2, but the height is always 1. So the hypotenuse for this right triangle is square root of 3. So that's the construction of square root of 3. If you sketch that on the x-axis or real line, all you need is just make another circle, right, centered at the origin, and length for the radius is that one, right? Then this is the matching point for square root of 3. So if you're just doing that, then all these points are assigned to that rational numbers. Okay, nice. Now there is another one you can do that. This one, actually, Pythagoras constructed this one like that. So in the beginning, just imagine that is right triangle with 1 and 1, and this is square root 2. Then simple Euclidean construction, you can make a line segment or line perpendicular to this line, right? Over here, right? And with length 1, right? Then this length becomes square root of 3, because in this right triangle, the hypotenuse length must be square root of square of one of them plus square of the other legs, right? So it's going to be 2 plus 1, which is square of 3, right? Now then you see the pattern, right? Sketch the another perpendicular line segment whose length is 1, then that becomes square root of 4. Actually it's 2, right? But just keep doing it. then that is square root 5, square root 6, square root 7. In this manner, if we just keep doing it, okay, then we can just sketch the line segment whose length is square root of n. So there are many different ways to sketch it, okay, like this. But now we have, why do we need square root of 2? That's the most important thing, right? Because in our number system, it's just rational numbers, then there is kind of gaps in there. Okay? So to fill this gap, like in real lines, right? If you're only accepting rational numbers, then there are many gaps, right? And these gaps must be filled by that irrational numbers, right? So we are wondering, okay, how can you sketch? How can you find that position? And one way is like this. There are many more, much more, right? So it's this explains, okay, how to get that algebraically, right? What is going to be value? It's a 1.414 like that, right? But what is the geometric representative of that? The length, the construction of it. You can do this way, or the ones you got the other one. You can find that in the link at the homework, right? Bottom of the homework page. But let me ask you one interesting question. You're going to get this one later, okay? Maybe 4,000 level or graduate course. You might have this question. Let's say between 0 and 1 is a combination of rational numbers and irrational numbers, right? And they are well scattered enough, right? So let's just assume, like, we just collect all rational numbers, actually collecting the points assigned to rational numbers and put them together in nice order, okay? And put all these the points assigned to irrational numbers and over here, okay? Collecting on this. So these are the collection of points assigned to rational numbers, and these are points assigned to irrational numbers, right? Now, what is going to be the length of each of these? One condition is, when you add them, the length must be 1, right? Because we are not adding new points or deleting any points, right? It's exactly the same points like that. So when you add this length, it must be 1. So the question is, how much, right? Each. And it turns out that this length is 0 and that length is 1. Now you see how big these irrational numbers are compared to the number of irrational numbers and rational numbers within that small line segment is almost 0 to 1. So then that much we have much more irrationals out there. So now you see the reason why we have to adding more of this number system, right? So eventually we are going to get real numbers by that. So finally we have our whole number. Then you might wonder, who says real number is enough, right? And who knows, right? This whole point is assigned by real numbers, which means there is nice one-to-one correspondence between the points on the real lines and the elements in the real number sets, right? And it turns out that yes, there is one-to-one nice correspondence. So which means if you're using real numbers, then and assigning to each of these points, there is no missing point or no missing elements from real number set, right? They're nicely matching each other. Okay, so that's the meaning of complete. There is no horse, okay? Which means in nature, real number is enough. But later, historically, we need that the imaginary numbers, right? So that's the title of why we name that way, imaginary, because it's not, it doesn't look like real stuff, right? But it's still needed to handle certain things. Okay? So later, in a later chapter. So anyway, in real number system, and that should satisfy these 8 axioms. And actually, you can break down some of these into 2 parts and something like that. So some books has looks like more conditions, but eventually it's just same as this one. Okay? So commutative. So this one, to say this one, we need to assign the addition and multiplication, that two operations within that set are. Okay, so we consider all together like that, right? Then we have to find out how we get this result, right? Then first thing is, whenever you need to calculate this, the answer must be again the real numbers. If it's not, you cannot control it, right? Some of them are kind of escape from that real set, right? Then you cannot handle it. So that closeness for operation is one really big needed condition. But after that, how can you define it? It's just you define it, but it must satisfy the commutative, right? And associative for addition and multiplication separately, right? So some books are separate this one into two statements each, but all together. And distribution, that's huge. And identities for additive and multiplicative. And because of that, we should expect the inverse of each, right? And because of those inverse of each operators, we need the negative numbers, right? And we need that quotient, right? So because of the inverse of multiplication, it requires that fraction forms, right? Other than that, just the integer is enough. Okay. And to defining the positive numbers, okay? And that positive numbers only is also closure for these two operators and like that. So this portion is just beyond our ability, right? But please just taste it, and in the later advanced course you are gonna see these steps. Okay? But that should be enough. So now you have the complete system of numbers up to real numbers. Okay, so be ready for that. Okay, the next one, the homework, just to do this, okay? And just to try to follow the answer. And if you want to see that other steps, and in almost all chapters there are some references and there are many links, right? And I believe you already checked those, so it's going to be very helpful if you check these steps, right, to study each chapter.